Welcome to this new tutorial about importing data into Cancha. I'm going to make this a quick video just to give people who haven't got a lot of experience dealing with geometallurgical data a quick background and how different data types are used and how you should be formatted to bring them into Cancha. So without further ado, we're going to be working this data tab to start with. This is where we import data. Here in the plus symbol is to bring up the wizard to import information, and you choose which data you need. I've already imported these data types here, but over here on the side here you've got templates for the data that you could bring in. So those templates are basically even a block model for drilling or for met samples. Let's have a little look first at the block model one. So this is what you would open up if you just get that standard, click on the button and get the standard file. There's a header page. This is basically just to keep good housekeeping for your files. It wouldn't be used by Cancha. It's always a good idea to keep what the project is, what the study is, what version, date, author, notes on revision. Standard for any engineering. Glossary is a good idea for block models. Usually they're using strange abbreviations and field names, and so it's a good idea to have a page here explaining what the different codes mean. And then for the actual data, the data that Cancha uses, it would be in this format here. So it's always going to have the northing, the easting, the RL for each block, and then fields. So the northing, easting, and RL basically define the corner of each block in the regularized block model. Let's just switch into Cancha quickly and look to see what am I talking about. So I'm just going to click on the bounds and click on the block model here, and then come out of bounds, and that's going to put the focus on this block model I've got here. I've already been playing with it, and I've got some of the different grades blocks turned off. So basically this is a synthetic block model, and you can see that all the blocks are the same size, and it's put together in a regularized way aligned with the northing and easting and the RL axes. So that's basically the northing, easting, and RL that we talked about previously. It's basically defining the lowest value in each block. It's not the centroid, it's the smallest easting, the smallest northing, and the smallest altitude. So this corner here defines this bigger block. And then afterwards you've just got fields, okay? So for example, at the moment we're showing the copper grade. But you could have a whole bunch of fields. You could have different lithologies mapped, you could have different different elements and different destinations, for example, whether it's going to leaching, flotation, or waste. Now whether it's in pit or out pit could be mapped into each one. And the way you would map that is by working with the mining engineers to fill in these different fields here. So there's no limit to how many different fields you can have. That's how a block model works. The next thing to look at would be drilling. Okay, so let's just go back on the bounds and we'll jump over to a drilling here. Made up again a fictitious drilling set. Click on that and bring the zoom in here. So these are fictitious drill holes. Let's turn off the samples for now. So each of these little pyramids represents a drill collar. A drill collar is the point where the drill rig was situated, and it was from there it drilled into a different trajectory. You can see that you've got a whole sphere around that point that you could drill into. So let's just go look at an example here. So when we've got the drill collars, that defines the point northing, easting, and RL, the exact point where the drill rig was situated. The hole ID is an individual name given to each hole. It has to be unique, and it has to be the same in every table. You can't call it TUT01 in this table and then go to surveys and have them called something else. It has to be the same, otherwise it's not going to work. Northing, easting, RL. And it's good to put the depth there, just for how deep the hole was drilled. If you don't have a survey of your hole, you can also put azimuth and dip, okay? Otherwise, the azimuth and dip would come into the surveys table, where you've got the orientation and attitude of each part of the hole, where they've come later and they've surveyed down the hole. Now, let's just go into the 3D here and explain a little bit about what that means. So we're on plan view, looking from above, and first of all, I'll just pick one that's heading north, right? So this has been drilled towards the north. And you can see here, this has got an azimuth of 0. So the azimuth is relative to north. What angle is that? It goes around with a clock, of course. So for example, one that's heading directly south, it's got an azimuth of 180. One that's heading up over in this direction, an azimuth of 40. Okay, maybe here, 320. 320 because it's come almost all the way around the circle and heading off into the northwest direction. So that's azimuth. It's the angle from north round to the way that the drill hole's pointing. The other thing we have to look at is dip. Okay, now the dip of the one that I selected just now is 0, and when I look at it from the front view, you can see it's going completely flat. So it means it's not dipping down at all. This one here is going straight up, so the dip is 90. It's from the surface, it's going 90 degrees straight up. Most holes would head down. Going directly down is minus 90. It's from the horizontal, it goes exactly 90 degrees negative. Okay. And then ones that go on an angle, this has got a dip of 30 degrees positive, and over here we've got 30 degrees negative. And so it's always from the horizontal, so it's always a small angle. So a dip should always be between minus 90 and plus 90. You're never going to get numbers bigger than 90, because then you'd be changing azimuth. Okay, so hopefully that's a good explanation of dip and azimuth. Now let's have a little explanation about the survey. So you can see that some holes here, they've got a kink in them. Because of lithology and faults and things like that, when they're going down the hole, it might have started on one direction, but then at a certain depth it changed directions. It changed dip and changed azimuth. So basically what we do in the 3D software is that we look at, for example, this one here, for example, it started off in this direction and then changed them in that direction. So that's what the survey table is. Let's just have a look at the table view. So we've got, different depths. We've got different azimuth and different dips. So you can see that in this case, the dip and the azimuth have been changing as it goes along. Further down for the holes 10 to 20 in this example, they've all got the same. It's azimuth and dip is the same, the whole depth, the whole way down. And so when we look at that, you can see that they're just straight over here. These holes here are just straight. Okay, so that's drill holes. Now lengths, interval data. You can see that here we've got intervals of 100 meters each. So let's just take an easy one. Take this hole here. You can see here on hole 14, we've got 2 sections. We could measure that. So from the drill rig, it came down. Maybe try again. Let's put it. Always good to click on that button there to have it exactly facing the camera. So now if we measure from the drill collar down, you can see that it's exactly 100 meters to the intercept. So we've got 100 meters there and 100 meters there. And this is 100 meters of interval data. So let's have a look at the gold here, and get the gold table view here. We can see that on hole 14, we've got 100 grams a ton between 0 and 100, and 200 grams a ton between 100 and 200. Let's look at that on the log view very quickly. So we've got here the gold grade, and from 0 to 100 meters, we've got 100 grams, and from 100 to 200 meters, we've got 200 grams. So that's interval data. It can be numeric or it can be categorical. Let's have a little look at some categorical information here. So let's go to something that's got a met sample. Here we can see that for the metallurgical samples, we've got diorite here for this sample here. And this is from 11 meters to 22 meters for a length of 11 meters. So from the drill machine along the length of the drill, not to a depth, but rather along the length of the drill core, from the 11th meter to the 22nd meter, they've registered diorite for that interval. What does that look like in the table? So in the table, it looks like this. You can see the lithology here. And here we can see that, so for this sample, and for this phase, lithology, diorite. I've skipped a step. I haven't shown you the origin table for the metallurgical samples. So how's metallurgical samples organized? Well, you've got several tables. You've got origin, characteristics, and results, typically. So you've got phase 1, 2, and 3 in this case. So this might have been, for example, 2015, 2016, 2017. Maybe working over 3 years to do different test work. Maybe it's different drilling campaigns. Maybe it's just different laboratories using the same samples. But it's always a good idea to keep your metallurgical test work in phases to keep it well organized. The sample ID. So in this case, it's just the tutorial samples, but it says T for tutorial, A for phase 1, B for phase 2, C for phase 3, S for samples down here, and then a numerical order of samples after that. We say which drill hole it's from, and which from and to. So going back to the log view is a good way to look at it. So we say, okay, we've got drill hole 1 from 10 meters to 32 meters for a length of 22 meters of sample. That's TAS 001. Just go back to here, and we can see from 10 to 32, it's 22 meters of sample. Okay, so this defines where the sample is. Let's just have a look at that in 3D. We can see that sample is over here. Here's the sample 1 here. Okay, so there's that sample. No, I'm not talking about, I haven't turned it on. That's drill holes. Sample 1, there it is. Let's just turn on the samples now, them turned off. And click on that, and then we bring up that sample. So there we go. That's what it looks like in 3D. Okay. So there's the origin table. Each sample should be declared on drill hole from and to. Characteristics. So these are the sort of tables that should explain what the characteristics of each sample is. In this case, I've put them all in one table for simplicity's sake. But normally, if this is a commercial project, I would have one table, for example, of head assays, another one for geology, another one for mineralization, another one for QuemScan mineralogy or something like that, another one for geotech. So every kind of different way to characterize the samples that are going into the test, we'd have them on a separate sheet. And for each one, we'd say which phase, which sample ID, and then a bunch of fields as to what the values are, either categorical or numerical data. Results, the same. Now, the results are kind of similar because, again, it's categorical or numerical information that you're coming out with these results, usually numerical. But we keep them on a separate page because in Cancha later on, where we're trying to map these and try to come up with models, it's good to have them separated as being results rather than inputs. Good to keep your inputs and outputs in separate sheets. So basically the same thing, what phase, sample ID, and then the results. Okay. So now going back to Cancha, we've got these here. We've got the results here on work index. We've got the characteristics. I can see what lithology each of the samples is, and which alteration or which iron grade it is. And that's basically how we import the metallurgical test work data. So that's all I'll cover for now. This is a very short tutorial just on how to format your data. So let's just recap really quickly going through this Excel book. They don't all have to be in the same Excel book. You can have different Excel books, or you can have CSV files. For example, block models can be very large. They can have 600,000 rows, for example. So you might want to keep that as a CSV file. But basically, the top row is always the field names, and then after that, you've got the values, right? Don't have two rows at the front. Don't put, for example, units of measure. Don't put a header at the top. Just the field names up here, and then no empty columns, and just straight away, the data underneath it. So for drilling, you always want to have a colors table. You can, or if you've got the survey data, you can have surveys. Otherwise, you'll have to put the azimuth and dip in the colors table for a static value, and the holes will all be straight. Things like assays, lithology, alteration tables, which would be interval data for the drilling. A block model it's simple. It's just a northing, easting, and RL with a bunch of fields after that. Metallurgical samples. So first of all, you declare where the samples are taken from. You declare what the characteristics of the samples are in one or more tables. And then the same with the results. You don't have to have them all in one table. You could have one for recoveries, one for comminution, other things like that. But basically you're saying what samples, what results they were. And there should really only be one result of each type for each sample. So that's an explanation of how Cancha deals with importing data. Thanks for your time.